Previously, we discussed simple linear models, and we saw how to fit them using the method of least squares. In the simple linear model, we related the response variable y to a single independent variable x using a straight line. In practice, we know that relationships are generally much more complicated. So there's usually a predictor variable that we are interested in, a response variable that we were interested in, and we know that that is most likely a function of multiple predictor variables. It's unlikely that there's really just one predictor variable that we are interested in. So in this set of notes, we're going to look at what is called multiple regression, and multiple regression is going to give us a way to use multiple predictor variables to predict what's happening with a single response variable. And so that's what this is saying here in the general form of the multiple regression model. We know that in practical applications, our models are going to be more complex than that of that first order or that straight line variable, or that straight line model. So probabilistic models that contain more than one independent variable are what we call multiple regression models, meaning that they have multiple predictor variables. And right here we have the general form. So looking at this, you'll notice that the terms that are new are these. So if we have k predictor variables, what we had previously was just the straight line model, which looked at one variable. Here we have the other k-1 predictor variables that we might be interested in. And one thing that is going to change is before, when we looked at simple linear regression and we only had these two terms right here that we were interested in, we talked about beta 1 being the slope of the line. Well, as we add on more predictor variables, that actually changes a little bit. And so what we're going to say here is bi determines the contribution of the independent variable xi. Now, in terms of the independent variables, or the predictor variables, they can be functions of other variables as long as that function does not contain unknown parameters. So some examples that you might see, and we're going to talk about this further later on in the course, is we might define x1 to be equal to the square root of some variable, or we could define, let's say, x2 to be equal to the cube of another variable. These functions are perfectly fine, and we'll look at them in more detail later on. But one thing that we could not include would be something like x3 is equal to x to the beta. And that's because this function does contain an unknown parameter. So generally, when we look at terms, things like x2 equals x1 squared, these are what we call higher order terms. So when we start squaring things or multiplying things together, we'll call them higher order terms. Or we could look at coded variables, which are things like this. And this coded variable is actually how we're going to handle categorical independent or predictor variables. And we're going to discuss both of these cases in further detail later on in the course. So here we just have a summary of how multiple regression models are analyzed, and you're going to notice this is very similar to the idea of simple linear regression. We're still going to collect a sample, we're going to hypothesize a form of the model, we're going to estimate our parameters, we're going to talk about the estimates of the variance, we're going to evaluate the utility of the model. So really all of these things are pretty much the same as what we looked at before. It's just now our model has changed, so some of the ways that we evaluate the model will change as well. Now the next section we have here is the matrix representation of multiple linear regression. Again, you're going to see this is very similar to simple linear regression. So I'm actually going to have you read this section on your own, as well as the next section, which involves the model assumptions. And again, these are very similar to the model assumptions that we saw with simple linear regression. And we are going to come back to the idea of checking and validating the model assumptions later on in the course. Alright, so we're going to skip down to the first order model with quantitative predictors. So a model that includes only terms for the quantitative independent variables and does not include any higher order terms. So again, those are terms like x squared, x cubed, or even it could be x1 times x2. So the first order term means that each x in the model is raised to the first power. And so here's a first order model with 4 quantitative independent variables, and notice we have those right here. The other thing to notice is I am calling this the model because I have the expected value of y right here. Just as a reminder, alternatively we could write the model as follows, and it would be just as valid. So instead of having the expected value of y on the left-hand side of the equality, we have y, but what that means is at the end of the model, we have to have the epsilon. So either one of these is an appropriate way to write the model statement. So we're going to talk about the first order model with 2 quantitative variables. So those are going to be x1 and x2. And for this model, the independent variables do not depend on each other. So let's talk about what that means in terms of an example. So suppose we have this model, and we're going to go ahead and give you the values of the parameters. So we have beta naught equal to 1, beta 1 is equal to 2, and beta 2 is equal to 1. That gives us this model. So let's look at what happens as we change the value of x2. So we're going to start out for what happens when x2 is equal to 0. So notice when x2 is equal to 0, we're going to have the following. We're going to have 1 plus 2 x1 plus 0, which is equal to 1 plus 2 x1. Now let's look at what happens to the model when x2 is equal to 1. And when x2 is equal to 2. So notice when we fix x2 at different values, what is happening is for each of the fixed values of x2, we actually end up with a straight line, and so we've seen equations like this before. And what I would like you to note is if we look at the comparison of these 3 lines, notice in all 3 lines, x1 is multiplied by 2. In other words, the slope of all 3 of these lines is the same. The only thing that changes is this piece right here, which is the y-intercept. So we can look at a graph of the lines and notice that these lines are all parallel. So what we're saying here is that the value of x2 does not change the effect of x1 has on y. And notice that that effect of x1, the effect that it has on y, that effect is measured, that should say which is measured, by the slope of x1. So in other words, notice here again, the lines are parallel, so the slope is not changing. The only thing that's changing as we look at different values of x2 is the y-intercept of that line. And later on in the course, we're going to talk about the idea of interaction and whether or not 2 variables interact with one another. And what we're going to see later on in the course is when variables have interactions with one another, we do not end up with these nice parallel lines. Those lines actually intersect one another. All right, let's look at another example. Professor Seth Stevens-Davidowitz studies the level of racial animus across different areas in America by measuring the percent of Google search queries that include racially charged language. A measurement animus is derived from his algorithm, and it is scaled between 0 and 250. And you can read more about it here at this website. The dataset contains observations from 196 different media markets, and we're going to look at a regression model to relate the following dependent variable y to 4 different independent predictor variables. So notice here are our 4 different independent or predictor variables, and we have that single response. So we're going to suppose that the model equation is as follows. So one thing to notice here for this example, I am giving you the parameters. So these these values that you see here, these were not derived from those 196 data points. These were not estimated using data. These are the actual these are the actual parameters, not the parameter estimates. So really what I'm doing is I'm giving these to you hypothetically, because normally we wouldn't actually know what the values of the parameters are. So but for this example, we're assuming that these are the actual parameters. This is what's actually happening in the population. So our first question here is, what is the deterministic portion of this model? So notice here, when we talk about the deterministic portion of the model, what we're really talking about is all of this. And recall, this comes from back in our earlier notes when we first learned about simple linear regression. So our deterministic portion is as follows. And then notice it says next, what are the values of the population regression coefficients? In other words, it's asking for the values of the parameters. And since I have given you the model, you actually know the values of the parameters. So these are not estimates that you would get from the data using SAS or R. I'm saying this is what's actually happening in the population. And again, this is a hypothetical example. And so again, notice I'm actually using the notation for the parameters. I do not have hats on top of these because these are not estimates. I'm saying these are the actual parameters. So let's interpret the value of the parameter beta 1. And so notice here that beta 1 is equal to 0.51. So the interpretation of beta 1 is going to be as follows. So I'm going to write it down and then I'll talk about it. So what you're going to notice is that the interpretation is very similar to the interpretation of the slope in simple linear regression, with one difference. So looking at the interpretation, we have the average median market animus measurement increases by 0.51 when the percent of African Americans living in the median market is increased by 1%. So if we stopped at this point, we would have the same interpretation of the slope when we worked with simple linear regression. The difference is this last part. So notice we say here that the other three predictors are held constant. So when we interpret beta 1 in a multiple linear regression model, and this is a multiple linear regression model where, if we go back up here, remember that we are looking at the model, the first order model with quantitative predictors. So be careful there. Later on we're going to introduce what are called interaction terms and higher order terms, so this will change slightly. But we say that the other three predictors are held constant. Alright, so the next one says interpret the value of beta 3. So pause the video at this point, see if you can write down the interpretation of beta 3, and then come back and we'll see if you get the same thing. Alright, so let's look at the interpretation of beta 3. So notice beta 3 is equal to negative 1.96. So the interpretation of beta 3 is going to be very similar to our interpretation of beta 1. We're going to start out with the average media market animus measurement. This time it's going to decrease by 1.96 when the percent, and notice this time we're interested in those with at least a bachelor's degree living in the media market. So we're going to say when the percent of those with at least a bachelor's degree living in the media market increases by 1%, and the other three predictors are held constant. So your interpretation of beta 1 and beta 3 are going to be very similar. The main differences are going to be, one, the value here, because you're going to want to put in the value for beta 3 instead of beta 1, and then the reference to which independent variable we are looking at. So for beta 1, we were looking at the percent of African Americans living in the media market, whereas for X3, we're looking at the percentage of those with at least a bachelor's degree living in the media market. Now we could ask questions like, what is the mean value of animus when? And notice we're given actual values for the 4 different independent variables. So to calculate these, we're going to use the model that we are given. So here we're going to have the expected value of y, which is, again, that is an average. That's what we mean by the mean value there. So we're going to have 124.2 plus 0.51 times the value of x1 that we have here, minus 0.62 x2, and x2 is equal to 9.4 for this part, minus 1.96 times the value of x3, and then plus 1.52 times the value of x4. And if you put that in your calculator, I believe you should get 85.727. All right, our last question here says, if repeated observations on rating are made on different individuals, all of whom have the same values specified in part E, in the long run, approximately what two values will 95% of animus values be between? So to answer this question, we always have to keep in the back of the mind, one of the assumptions that we have is that those errors are normally distributed. In other words, how far we move away from our prediction is normally distributed. So if we're interested in 95%, we can apply that empirical rule that we mentioned earlier on in the course. And remember that the empirical rule tells us if something is normally distributed, we anticipate 95% of the observations to be within 2 standard deviations. So since we make that assumption that our errors are normally distributed, if we look at our mean value, which in the previous part we got was 85.727, then we know 95% of the values will be within plus or minus 2 times the standard deviation. Now at the very beginning of the problem, one of the pieces of information we were given is that sigma is equal to 5. So what this tells us is that 95% of the values are going to be between 75.727 and 95.727. And again, that's by application of the empirical rule because we make the assumptions that our errors are normally distributed. And that's going to end this note set. We're going to continue looking in future note sets more at the idea of multiple regression.